All right, so again, as in 583, there's a sort of an approximation that's going to be happening here. But so let's see here. So we have a curved path C. So let's say here's the ground, and my tree is, let's say that's my tree. So, some sort of a bendy kind of weird-looking tree like that. So this is our path C. And the thickness isn't constant, but the cross-sectional area, so let me see if I can't draw so here's the thickness of the tree, like that. And the cross-sectional area at a particular point, if you look at a particular point there, that cross-sectional area is given by some function A that depends on X, Y, and Z. There's a formula for it there, right? Okay. So the idea is we want to write down a scalar line integral to write down an expression for the total volume of wood. Okay, well, the total volume of wood is going to be a scalar line integral of the little pieces of volume of wood that you would associate to a particular cross-section. And at some particular cross-section, there's a little piece of volume of wood, and that dV, I claim, is going to be the cross-sectional area times ds. Namely, ds represents the corresponding length of that little piece of curve. So this just becomes integral over the curve A ds. And let's see, we have a formula for A. This is 1 over 1 plus the square root of z ds. There you go. Does that make sense?
And that's it?
That's it for the first part, because notice I didn't ever tell you anything about the curved path C. And also the problem says, use the notation of a scalar line integral. It didn't say to, parameterize and, evaluate or write it as a single variable integral. We're just leaving it as a scalar line integral. So there you go. And we can't go any further because we don't know anything about that curve. Right. Now you're right that number 2 is very closely related. Let me go ahead and do this one with the same little bit here. So same setup, got the same tree. Now we've got bacteria that are going in, and the only difference here is that instead of computing volume, we're going to be computing something that relates to volume, namely quantity of bacteria. And those things relate by, let me again look inside of one of these slices in here. Let's see, I didn't make any choice of notation for bacteria. Let me use B to represent the quantity of bacteria. So I'm going to say dB represents the amount of bacteria in that little slice of wood. Right? So, all right, so the total amount of bacteria is, well, I have to add up over all the pieces of curve the associated amount of bacteria that I associate to that piece of curve. And in any piece of curve, the amount of bacteria is what I'm calling dB, and that's going to be the volume times the concentration. So this is this concentration function, C of x times dV. Oops, sorry, there. So the amount of bacteria in there is the concentration times the volume in there. Does that make sense? Okay. So with that being said, I can rewrite this as concentration times dV, but wait a second, we already know this is integral over the curve. dV is A of x ds. And so there's a scalar line integral representing this next answer. And you're absolutely right. I mean, there is an approximation going on. The concentration is technically not exactly quite the same there as it is a little bit slightly over in that same slice. But so that's the component of the approximation we're talking about. Yeah.
Thanks.
Yep. Sure. Anybody else? Does that make sense to everybody? Yeah. Oh, next question. Okay. Hang on a second. Let me stop this recording here.